Hello, friends. Today we are continuing with topic 213. This is part two. Actually going back, if you're watching this in order, I forgot to record it earlier, so I'm doing this now. But we're just continuing with this idea of finding inverses of functions, right? Exponential, logarithmic, and then we're going to introduce the idea of inequalities. Also relying a little bit on some of the other stuff we've done in the past, a little bit of review, rational expressions, etc. Okay, so we're still using the general form of the exponential function, right? A times b to the h plus x plus k. So this is how we leave our log or exponential functions, and logarithmic functions can look like this, right? And so what we do in order to solve is we switch the x and the y, and then we just solve for y the way we would otherwise. And so here it says find the inverse of this function. Okay, so I'm just going to rewrite this as y equals 3 times 2 to the x plus 4 minus 15. And so what do? I switch the x and the y. So I write x equals 3 times 2 to the y plus 4 minus 15. Okay, so first thing I'm going to do is I'm going to add 15 to both sides. So I get x plus 15 equals 3 times 2 to the y plus 4. I'm going to divide both sides by 3. So I get x plus 15 over 3 equals 2 to the y plus 4. Now I'm going to take the log of both sides, or rather rewrite this in logarithmic form, I should say. So this is log base 2 of x plus 15 over 3 equals y plus 4. And now I just solve for y, subtract 4 to both sides. So y equals log base 2 of x plus 15 over 3 minus 4. And that's it. That is the inverse of f of x. So I can write f to the negative 1 of x is log base 2 of x plus 15 over 3 minus 4. Okay. Now it wants us to find the inverse of this function. So now instead of going from an exponential to a logarithmic, practicing going from a logarithmic to an exponential. Same idea. So I write y equals negative 3 log base 5 of x minus 4 plus 6. Switch the x and the y. So now I have x is negative 3 log base 5 of y minus 4 plus 6. Now I'm just solving for y. So first thing I do, I'll subtract 6 from both sides. So x minus 6 equals negative 3 log base 5 of y minus 4. I'm going to divide both sides by negative 3. And so then I'm going to get x minus 6 over negative 3 equals log base 5 of y minus 4. I don't like to leave negatives hanging out front. So what I'm going to do is I'm going to rewrite this as 6 minus x over 3. So now I can switch to exponential form. 5 is the base. The exponent is 6 minus x over 3. That equals y minus 4. Add 4 to both sides, so I get y equals 5 to the 6 minus x over 3 plus 4. So the inverse function of g is 5 to the 6 minus x over 3 plus 4. All right, for example 3, here they give us a function, and then they tell us that k of x is the inverse of h of x. So we've got k of x and h of x, they're inverses of each other. It says for what value or what values of x does k of x equal 1? Okay, so I'm saying if we think of it this way, that, you know, k of x equals y, right? So instead of writing k of x, I can write y. The question is, for what value of x does y equal 1? So what we're saying is, when is 1 the output of k of x? Right? Well, then if 1 is the output of k of x, that means 1 is the input of h of x. And then whatever I get from h of x, it should give me what I'm looking for, the x input for k of x. Let's put it this way, right? If we make a table h of x, and then over here is h inverse of h of x, or in other words, k of x. Okay. So if there's some value that this is equal to, right over here, let's say this is s, and then over here is p. What this is asking for is what is the p, what is the input that gives me this output for k of x? That's what it's asking for, right? I want to get 1 as the output of this function, right? So what do I put in here to get 1 to come out? Well, because I'm dealing with the inverse, I can just take 1 and put it into h of x, and it'll give me the output. And that output would be the input for the inverse function, or the k of x. So all I have to do really for this is I take 1 and I plug it into h of x. So h of x equals 3 to the 1 plus 1. Rather, I should write, instead of writing h of x, I should write h of 1 to the 1 plus 1. 3 to the 1 plus 1 minus 2. So 3 to the 1 plus 1 is 3 squared. So that's 9. 9 minus 2 is 7. So the answer is, k of 7 equals 1. That's the answer. 7 is the input of k that will give me an output of 1. So what you could do, you could just take the inverse of this. You could just go ahead and take the inverse of h of x, find that, and then set it equal to 1, and then you solve back to x. But in that case, you would just be undoing everything you just did to find the inverse, because then you're finding the inverse of the inverse when you end up solving for x that second time. But you can think of it in terms of what the inverse is, the input, the output. It'll simplify it, and you can solve this much more quickly. All right, now with inequalities, you've seen inequalities before, and it works the same kind of way. Just keep in mind the algebra rules, and then how the output input works for logarithmic functions. Let's go ahead and start this one. We'll see. So we're going to simplify this. I'm going to rewrite this as f of x is log of, I'm going to use the quotient rule here. So this is x squared minus 4x plus 7 over x plus 3. Okay, so now I want to find what are the values of x for which f of x is greater than 0. So I'm looking to see when is this greater than 0. Okay, so if in order for the whole function to be bigger than 0, again, keep in mind this is the exponent. So I've got 10 to some number that's going to give me something in here. Right? Well, 10 to the 0 is going to give me 1. So for any value of 0, or any value bigger than 0, then this thing here has to be more than 1. So I'm going to rewrite this as x squared minus 4x plus 7 over x plus 3. And this is going to be bigger than 1. I'm looking for the places where that's bigger than 1. So let's solve this. Basically solve for the values of x that we're dealing with here. So I've got x squared minus 4x plus 7 is greater than x plus 3. So I multiply both sides by x plus 3. Now I subtract x, subtract 3 from both sides. And I get x squared minus 5x plus 4 is greater than 0. Right, so I'm finding some zeros. By the way, I also have the 0 of -3. Or rather, -3 is a place where, this thing can't exist. It's not a 0, it's actually an asymptote. But the point is that it can switch value, positive and negative, right? So let's see. In that rational expression, we're looking for our zeros, and then that's a place where, because we're looking to see where can it be more greater than or less than zero, positive or negative, etc. So anyway, now I factor this, and I get x minus 4 and x minus 1. Where is that greater than 0? And so my zeros here are 1 and 4. So negative 3, 1, and 4. So now we create the number line. This is some good review from earlier. Okay, so I'm going to have negative 3, 1, and 4. So we're going to plug in some number less than negative 3, something like negative 4. When we plug negative 4 into this, what I end up with is a negative number. So negative. And then anything bigger than negative 3, this ends up being just positive 1. So then anything bigger than negative 3, so from between negative 3 and 1, so let's say something like 0. If I plug in 0, I end up with a negative and a negative. So this gives me an overall positive value. And then between 1 and 4, if I plug something in like 3, then I get this would be negative and this would be positive. So I get overall negative. And then if it's bigger than 4, everything turns out to be positive. And so I'm positive in that region. So it's here and here. These are the places where f of x is going to be bigger than 0. And so I can note this as, from negative 3 to 1 and 4 to positive infinity. Okay, interruption, change of venue, but we're good. So let's take a look at example 5. What we're doing here is that we've got an inequality, but instead of just where a function is less than 0, we're looking at where one function is less than another. So first of all, domain check. Where are these functions defined? So h of x, natural log of x plus 4. So x plus 4 has to be greater than 0. And so here, this only exists where x is greater than negative 4. Okay, that's our first domain. So, and then g of x, we're looking for, so natural log of x squared plus x minus 5. So we're looking for the place where this, x squared plus x minus 5 is greater than 0. So we have to solve this. And this gets messy. We use a quadratic formula. And what we end up with is x has to be less than, right, so we're looking for the places where it's greater than 0. So, separating it out and finding where our zeros are. And so x has to be less than negative 2.7912, or x has to be greater than 1.7912. Okay, when we use quadratic formula, that's what you get. So these are our domain restrictions. Okay, so now what I do is I take these two and I'm going to have g of x is less than h of x. And so I bring them together on one side. G of x minus h of x is less than 0. Well, the thing is, since these are logarithmic and natural logarithmic, in fact, I can combine them and turn them into one logarithm. So this becomes natural log of x squared minus x, that's not an x, x squared minus x plus x minus 5. I'll get it right eventually, just stick with me. X plus 4 is less than 0. Okay, so now this works when x squared plus x minus 5 over x plus 4 is less than 1, just like we had done before. Okay, so now I'm going to x squared plus x minus 5 is less than x plus 4. When I subtract x and I subtract 4 from both sides, x minus 4, then I get x squared minus 9 is less than 0. So this is true when x is positive 3 or negative 3. And so x plus 3 is less than 0. And so what I've got is this number line. Our domain starts at negative 4. Then we have a 0 here at negative 3. And then I have 2.7912, negative 2.7912, and then positive 1.7912, and then I have positive 3, and then anything bigger than that. This region in here, I'm thinking no domain, right? So really I've just got 4 regions I'm checking, here, 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 and here. So if I plug in something like negative 3.5, then both of these end up being negative, and so I get a positive value, overall positive value here. And then it's negative here. And then in this region, this is negative as well, and then positive after that. And so I'm looking for the places where this is less than 0, right, where it's negative. And so the answer that I get, not a great use of space, but I'm going to go over here. So this is true when x is between negative 4 and negative 2 point, what's that number? 7912, or positive 1.7912 and 3. So those are the intervals where g of x is less than h of x. Last example. Let's take a look. So we're looking for the places where k of x, so 1 minus 4 times 2 to the x minus 3, where this is less than or equal to negative 31. Right? And now I just solve for x from this. Okay. So I'm going to add 1 to both sides, or subtract 1 from both sides. Divide by negative 4. Now don't forget, when you divide by a negative number, it switches the sign. So this becomes 8. So now I can write log base 2 of 8 is greater than or equal to x minus 3. Log base 2 of 8 is 3, right? 3 is the exponent of 2 that gives you 8. So 3 is greater than or equal to x minus 3. I add 3 to both sides, so I get 6. Okay, so this is true. K of x is less than or equal to negative 31 when x is less than or equal to 6. And that's it. So really just applying things that we know, things we've already done, and applying them to some new situations. Thanks for watching. Don't forget to like and subscribe.